Hey guys, welcome back to the channel. In today's session, we are going to cover the substitution method for solving recurrences. If you have watched other sessions on recurrences, I covered master method before this session, and substitution method is the second method for solving recurrences. So this is a very powerful method for solving recurrences, and it has two steps. The first step is we guess a solution for a given recurrence, and after that we use induction to show that the solution is correct. So the important part is we must be able to guess the solution, and which is not easy. With experience and looking at different recurrences, you will be able to start guessing solutions slowly and slowly. So let's look at a few examples so that you have a good understanding of how the substitution method for solving recurrences work. So we will start with a very easy example, and as we go, we will take a couple more examples which are a little bit more complicated to solve. So our first example is solving the recurrence for linear search. So the recurrence for linear search looks like and when we talk about recurrences, which are actually recursive functions, we talk about a base case. So the base case is, if you are watching my previous sessions, I talked about base cases, which means when the recursion should stop. And when I say t1 is equal to 1, this means if we have only one value or one index in the array, then it takes a constant time to find a value using linear search. So now let's try to solve this recurrence. So how we solve it is, we start with the recurrence, we try to guess a solution, and secondly, we also try to guess how this problem is being subdivided into smaller steps. So we know that doing a linear search actually takes a linear time. So let's guess our solution. Guess is okay. Now we start with our recurrence. Tn is equal to 1 plus t. We also see that the problem is reduced by 1 at every step. Okay, if we look at this recurrence, this means the problem size is reduced by 1 at every step. So at the first step, what we are going to do is we are going to calculate t n minus 1, and which will be 1 plus. So we substitute n minus 1 for every n, which will be, okay. So this is t n minus 1, and we are going to substitute this t n minus 1 here. So then our tn becomes okay, and this becomes right. So we are going to do these steps a couple more times so that we know how the reduction is happening, and we try to find a generalized equation. So now let's do it for n minus 2. We substitute n minus 2 for every n, which will be n minus 2 minus 1. So then tn minus 2 becomes sounds okay, and we are going to substitute this here. So then this becomes 2 plus 1 plus tn minus 3, and when we open it, this will be okay. Let's do one more step to generalize this equation. N minus 3 will be 1 plus, we will substitute n minus 3 for every n. N minus 3 minus 1. So then tn minus 3 is equal to 1 plus n minus 4. And we are going to substitute this here. So then this becomes 3 plus 1 plus t n minus 4. And if we open the bigger bracket, this becomes, sounds okay. So we can say for some value k greater than equal to 1, the generalized equation is going to look like k plus t n minus k, right? Because this is a variable and this is a variable, which are actually changing as we are reducing. So then we can change these to some value k. Now, what is our base case? T1 is equal to 1. This means if we make this 1, we are going to go to the base case, right? So what is happening? We started with n, then we did n minus 1, n minus 2, n minus 3, and we go until it's n minus 1, right? So we reach when this value or this value slowly decreasing reaches 1. So this means n minus k will be 1. Okay, and this means k will be n minus 1. We are going to substitute this in our generic equation. This will give us n minus 1 plus t1 because n minus k is equal to 1, and this will give us n minus 1 plus this is equal to 1 from the base case. And this will come out to be n. And I think that's what we guessed. So we solved our recurrence for linear search using the substitution method. Let's look at another example, which will be a little more tougher to solve compared to the recurrence for linear search. So the example 2 is for merge sort. And the recurrence looks something like this, which I think you must be familiar with. And the base case okay. Right. So let's do a guess. So looking at the recurrence, what can we guess? We know that the problem size is being divided into half. And when we divide the problem size into half, we know that the time complexity will be log n. And this log n is being done. When this is done, there is n work being done every time. So then, can we guess the time complexity will be n log n, right? Because if you watched my previous sessions, how does the code look like? If this is the merge sort function, we call the merge sort for n upon 2, and we call merge sort n upon 2, which is 2 times, right? That's why this becomes n upon 2. And then we do a merge step for 1 to n value, and this takes, right? So for every merge sort, we are doing n work. So from the code and from our experience, we can say, or we can guess, that the time complexity for this recurrence probably would be n log n. So that's how you are going to guess, and you will be getting better at guessing the solution to a recurrence as you do more problems, gain more experience, right? Okay, now let's try to solve this recurrence using the substitution method. So our recurrence is plus Cn. Okay, so we see that the problem is being divided in half. So we are going to do a couple substitutions by reducing the problem size into half. So the first step is we are going to calculate Tn upon 2, and which will be, we are going to substitute n upon 2 for every n in our recurrence. So this will be T n upon 2 square plus C n upon 2, right? And then we are going to substitute this for this, and we are going to get okay, let's try to reduce it. We are going to open the square brackets, and which will give us and this will be Cn plus Cn will become 2Cn. Okay, so that was the first substitution. Now let's do another substitution, which is T n upon 2 square, because when we divide n upon 2 by 2, we are actually dividing it by 4 or 2 square. So then this becomes n upon 2 cube plus c n upon 2 square from here. And then we are going to substitute this here. So then this becomes 2 square 2t n upon 2 cube plus c n upon 2 square plus 2 cn, right? Let's open, becomes this plus 2 square c n upon 2 square plus 2 cn. By doing this, we get plus cn plus 2cn 3cn. Okay. Okay. Let's do one more step to see how a general form of equation can be done. So t n upon 2 की power 2 cube is equal to 2t n upon 2 to the power 4 plus c n upon 2 to the power 3, right? And then this is going here. So this will become 2t n upon 2 to the power 4 plus c n upon 2 to the power 3 plus 3 cn. If I skip some of the steps, I am going to get right like our previous steps, the way we did. So then let's do a generic equation for a value k. We can say Tn would be 2 to the power k t n upon 2 to the power k plus k cn, right? This is variable, this is variable, and this is variable. Okay. Now let's do the base case. Base case says t1 is equal to 1. This means this has to be 1 because we keep on reducing n divided by 2, n divided by 2 to the power 3, n divided by 2 to the power 4, and slowly when we keep on dividing, there will be a value of k which will make this expression 1. Fine. So right, and by log property we can say okay, this means we need to divide n until log 2 n times when it becomes 1. I'm sorry, divide n until 2 raised to the power log 2n times until it becomes 1. Let's put this value in our generic equation, and then it will become 2 log 2n t, because n upon 2k is 1, we will say t1 plus log 2n cn. Because t1 is 1, we can say just rearranged the values or the variables. So what can we do? We can say this is n, so n plus cn log this, and we know that we can eliminate the smaller values because they does not add up to the time complexity. So we can say Tn is equal to Cn log base to n, and that is our solution to the recurrence for merge sort. What did we guess in the beginning? Okay, we guessed something like this. We missed the constant. That's fine. And this seems to be a solution using the substitution method. Let's look at another example. This is probably similar to our previous example we did, maybe a little different or maybe a little more hard to solve. So example 3, it is some recurrence. Okay, so the recurrence looks like when n is greater than 1 and the base case is okay. So our first step is to guess. Now, from our previous experience, this looks like the recurrence or the recursive call of merge sort. So we can say this could be log n, and we are doing n square work for every log n recursive call. So we can say this might be n square log n. Let's see if our guess turns out to be correct. So the problem is being divided into half. We are going to do a few steps which will divide the problem into half, and then we try to guess a generic equation. So let's do Tn upon 2, which will be 4Tn upon 2 square plus n upon 2 square. So we substituted n upon 2 for every n. Now we substitute this for this Tn upon 2, and we get 4Tn upon 2 square plus n upon 2 square plus n square. And this turns out to be 4 square Tn upon 2 square plus 4 n upon 2 square plus n square, right? Now if we see, we can reduce these values and we will get square plus square, and then this becomes plus 2n square, right? Okay, let's do the second step of substitution, which is n upon 2 square, right, for this, which will be 4Tn upon t cube plus n upon 2 square and whole square. Let's put it here, which will be 4T plus n upon 2 square whole square plus, okay, and opening the bigger square brackets, we get n square upon and this gives us and so finally right? So if we want to generalize this, for some k, what we can say is for k t 4 upon k plus k n square. Why? This is variable, this is variable, and this is variable, right? Let's do the base case. T1 is equal to 1, and we need to divide until this is 1, which means I need to do a little correction. I think I wrote 4 instead of n. N n n. Okay, so we will say n upon is equal to 1, or k is equal to log base 2 n. Putting this value in the equation, we will get 4 t 1, because this is 1, plus log base 2 n and n square. Simplifying this, we can say 2 raised to the power 2 t of 1 plus n square log 2n. Fine? Okay. So then this is n. Using the log property, we can say n square t1 is 1 plus n square log base 2n. And so, ignoring the lower values, we get and this is the solution to our recurrence using the substitution method. And did we guess this? Right? So these were a few examples to show how we can solve a recurrence using the substitution method. I hope this session gave you a fairly good understanding of how to solve recurrences using substitution method. In our next session, we are going to cover the tree method for solving the recurrences. I'm going to end this session here, and I'm going to see you in our next session. Thanks for watching, and bye for now.